Let us start a new section. This section is about the Möbius inversion formula, and we need to first of all define Möbius mu function. Suppose n is a positive integer, then mu of n is defined like this. If the input n is equal to 1, then the output is also 1. That is, mu of 1 is equal to 1 is defined to be equal to 1. If the input n, however, is divisible by the square of some prime number, then mu of n is defined to be 0. But if this is also not the case, then the input has to be a product of distinct prime numbers, p1, p2 up to pr. If there are r number of primes here, then mu of n is defined to be the rth power of minus 1. Now, before we see what properties this mu function has, let us see some values of mu. So, from this definition, we immediately see these things, that mu of n is equal to 0 if n is not square free. A square free number is an integer which is not divisible by the square of any prime. If n is not square free, that means if n is divisible by the square of some prime, then mu of n is equal to 0. But if n is square free, that is, if n is of this form, that it is a product of distinct primes, then obviously it is not divisible by the square of any prime. It is, however, divisible by these primes, but not their squares, not the square of any prime in fact. In that case, mu of n is minus 1 to the power r, if r primes are involved in this factorization. And then, what about the first few values of mu? So, these are the first few values of mu, but before seeing what they are, let us note this. This is a small example illustrating this part of the definition. Say you want to calculate mu of 30. 30 has this prime factorization 2 times 3 times 5. So 30 is a product of 3 distinct primes. So by the definition of mu, the mu value of 30 is the cube of minus 1, because the number of distinct primes here is 3. So the value is minus 1. Mu of 1 by definition is already 1, it comes directly from the definition. What is mu of 2? Note that 2 is also a number of the form 30. Yeah, it's true that 2 is prime and 30 is composite, but that's not the point. The point here is that 2 is square free, 30 is also square free. Both 2 and 30, none of them is divisible by the square of any prime. So by the definition of mu of 2 would be minus 1 to the power 1, because there is only one prime involved in the factorization of 2, which is 2 itself. Similarly, mu of 3 is also minus 1 because 3 is prime. Mu of 4, however, is 0 because 4 is divisible by the square of 2 and 2 is a prime. Mu of 5 similarly is minus 1. What about mu of 6? 6 is again a square free integer because it's 2 times 3, and in its factorization there are 2 primes, 2 and 3, so minus 1 to the power 2. That's why we are having 1. So like that the values go. In general, if you have a prime p, then mu of p is minus 1, like these cases. But if k is a positive integer at least 2, it's greater than or equal to 2, then mu of p to the power k is 0, because then p to the power k is divisible by p square, so the mu value is 0. Now next we are going to see the it's not exactly obvious, but it is something that we have been seeing for quite some time now, that the functions we are considering, all these sigma, tau and other variants of these functions, they have all been multiplicative functions. Mu is also a multiplicative function. That's what we are going to see next. And that result is theorem 6.5. And the statement is just that. The function mu is a multiplicative function. Let us now prove this. So the proof obviously is going to start by considering two positive integers m and n, which are relatively prime. So we need to, you already know what we need to do. We need to prove that mu of mn is equal to mu of m times mu of n. So let us first see the easy cases. What happens if m is equal to 1? In that case, mu of mn would be equal to mu of n because mn is equal to n, m is 1, which you can write as 1 times mu of n, and 1 is mu of 1, and then we have mu of n. So then that's how you have mu of m times mu of n. So at least in this case, our claimed identity is true, claimed equation is true. Similarly, if n is 1, then also this is true. You can go through the details, it's very easy. So now we can assume that m and n are both greater than 1 because they are positive integers. If they are not 1, then they will both be greater than 1. So we can now assume that m and n are both greater than 1. Now let us consider this next case. Say there exists a prime p such that p square divides either m or n. Suppose. Then obviously p square would also divide mn. There is nothing to say about it, it's obvious. But then mu of mn would be equal to 0 by the definition of mu, because mn is divisible by the square of a prime, so mu of mn would be equal to 0. And that is also equal to mu of m times mu of n. Why? If this is the case, then mu of m is equal to 0. Or if that is the case, then mu of n is 0. So anyway the product is going to be 0 in this case. So that means this case is also settled. In this case also our claim is true. So we can now further assume that not only are we having this, that m and n are both greater than 1, but both of them are square free. This is the case where at least one of them is not square free. So we are left with that only case now, that both of them are square free. Are we going to get our claim true in this third case also? Let's see. So finally, we assume that m and n are both square free. That means in their prime factorizations, only distinct primes will appear all by themselves. And by that, I mean that they will appear to the first degree. For example, p1 only occurs as p1, not p1 square, p1 cube, nothing like that. All these pi's in the factorization of m are distinct. Similarly, all the qj's in the factorization of n, these are all primes, they are also distinct. Moreover, something else is true. We should not forget that our integers m and n are relatively prime. So there is nothing common between these two factorizations as well. No pi is equal to any qj because of this condition. So then what can we say about the product of m and n? So the prime factorization of mn is this times this, where now also we have distinct primes. How many distinct primes do you see here? The number is r plus s. Why is it r plus s? Well, you already had r distinct primes in the factorization of m, and now you have s distinct primes in the factorization of n, and there is nothing common between these two lists of primes. So the total number of distinct primes is r plus s. So what is the consequence of all this? Now if we calculate mu of mn with the knowledge that mn has a factorization like this, then obviously the value will be minus 1 to the power r plus s, because just like m and n, the individual numbers, mn is also square free and it's a product of r plus s distinct primes. That's why minus 1 to the power r plus s. But then that is equal to this minus 1 to the power r times minus 1 to the power s. This, however, is mu of n and this is mu of n. So in this third case also, our claim is true, and that is why the function mu is multiplicative. And let me end the video here itself. We will see why we are seeing the title of this section, Möbius inversion formula. What are we inverting? What are we going to invert? Yes, we will invert something, and we are going to do that with the help of this function mu. And in fact, it may look a bit strange. I mean, in the beginning itself, without any motivation or anything, suddenly we just introduced a strange function mu. This strangeness was not present when we introduced the functions sigma and tau, because they were something very natural. Tau calculates the number of distinct positive divisors of a given integer. Sigma calculates the sum of those positive divisors. This, however, is a bit strange. Suddenly, why 1, 0 and -1 to the power r? We will see why it was chosen and what it's ultimately going to give us. But that we will do next week on the same day. So see you next week with more things on this. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.